Okay. So, today's class we will look at two examples of applications of all that we have learned so far in linear algebra, especially an application of matrix methods. The two applications that we will talk about today are Slater determinants and Huckel molecular orbital theory. Now, Slater determinants is the first application that we will talk about. And Slater determinants are used to express wave functions of many electron systems. And by many electron we mean more than one electron. So, a system with more than one electron, the wave function of that system is expressed in terms of Slater orbitals, okay, in terms of Slater determinants. So, how does this work? So, for this let us consider the case of a helium atom. So, the helium atom has two electrons. So, the wave function of the helium atom, the electronic wave function of the helium atom is a function of the coordinates of both electron 1 and electron 2. Okay. So, this is the total electronic wave function, and 1 is the coordinates (1 and 2) are coordinates of electrons. And when I say coordinates, I mean both the spatial coordinate, that is where it is located in space, and the spin coordinates and what its spin is. Okay. So, for example, electron 1 could be located at r1 with spin alpha, or it could be located in r2 with spin beta, and so the coordinates of the electrons have both the spatial and the spin part. Okay. So, now, in order to write the wave function of a helium of a many electron system, the first approximation that we make is called the orbital approximation. So, the orbital approximation consists of saying that this wave function, which is a function of both the coordinates, can be written as a product of coordinates of first electron and the coordinates of the second electron. So, in other words, you can write your wave function of 1 and 2 as a product of wave functions for the first electron, phi 1 of first electron, phi 2 of second electron, and so we say that each electron stays in its own orbital. So, electron 1 is in orbital corresponding to phi 1, electron 2 is in orbital corresponding to phi 2, and so this is the first approximation. This is called the orbital approximation. Okay. Now these need not be the same as orbitals of the hydrogen atom, okay, but this is some orbital, some atomic orbitals of that particular species of helium atom in this case. Okay. So, now there is a fundamental principle that says that your wave function psi of 1 2 should be antisymmetric to permutation of 1 and 2. So, the total wave function, this is the total wave function, has to satisfy the property that psi of 1 2 equal to minus psi of 2 1. Okay. This has to do with the fact that the electrons are what are called as fermions or spin half particles, and all spin half particles have to be antisymmetric to interchange of the two particles. Okay. So, this is a fundamental property of the system, and it's because we are looking at electrons that interchange of electrons should give the same wave function with the opposite sign. Okay. So, now what we are going to do is we are going to try to construct various orbitals that satisfy this property, or various wave functions that satisfy this property. Okay. Now, Furthermore, we write this total, the wave function of one electron. Okay, so the single electron wave function phi 1 of 1, this is factored into a spatial part and a spin part. So, I will call it psi spatial times psi spin. Okay, this is the, and the spatial coordinate of 1 is r1, and the spin coordinate I will call it s1. Okay. So this is written in this form, and so your total wave function, your psi of 1 2, can be written as psi spatial of 1 2 of r1 and r2 times psi spin of s1 s2. These are the spin coordinates. Okay, so just as you have spatial coordinates, you have spin coordinates for each of the electrons, and it is this total wave function that should satisfy this antisymmetric property. Okay. So let's start with this helium atom. Okay. Now since we can factor the orbital into a spatial part and a spin part, we can say that the spin functions are denoted by there are only two possibilities for these spin functions. The two possibilities are alpha and beta. Okay, so the spin function of any electron can either be alpha or beta. These are the two spin functions corresponding to, you can think of them as spin up and spin down. So there are only two possibilities for the spin functions. Okay. So now if you look at the total spin of the system of the 2 electron system. Now there are various possibilities. So for example, you could have the first electron in alpha. So the first electron is in spin state alpha, and the second electron is also in spin state alpha. Okay. So now both the electrons are in spin state alpha. Alternatively, you could have both the electrons in spin state beta. Or you could have one electron in alpha and the other electron in beta. So you could have electron 1 in alpha or electron 2 in beta. Okay. But because the electrons are indistinguishable, this should be the same as electron 2 in alpha and electron 1 in beta. Okay. So these two are actually, you cannot distinguish between them. So this sort of representation is not valid as a representation of the spin function of the 2 electron system, and you have to consider either a linear combination of this form, okay, or a linear combination of this form. Okay. And this function is symmetric to interchange of S1 and S2. So if I switch S1 and S2, this remains the same, whereas here if I switch S1 and S2, this changes sign. Okay, so this is anti-symmetric. To exchange of S1 and S2. Okay. What we mean by antisymmetric is that if I change S1 and S2, then this whole wave function will change sign. S2 beta S1 minus alpha S1 beta S2, that is negative of this wave function. Okay. Whereas these three wave functions, if I change S1 and S2, they are symmetric. S1 and S2. Okay. And we could not use this as a wave function. We could not use this as a valid wave function because it is neither symmetric nor antisymmetric to exchange of S1 and S2. And so we had to construct two combinations, one which was symmetric and the other which is antisymmetric. So these are the four allowed spin functions. So the allowed spin functions are these four. So if you say psi spin of S1 S2 can take any of these values. So these are allowed values for psi spin of S1 and S2. Okay. So now what we will do is we use these in a combination with a spatial wave function. Okay. Now since the product of the spatial times the spin part has to be antisymmetric, since this product has to be antisymmetric, it follows that if you take a spin part which is symmetric, then the spatial part has to be antisymmetric. Okay. And if you take a spin part to be antisymmetric, the spatial part has to be symmetric. So since this product has to be symmetric, okay, that means one of these has to be antisymmetric, the other has to be symmetric. Okay. Now there are three choices of taking symmetric spin parts. Spin functions, and there is only one choice of an antisymmetric spin function. Okay. So let us go and try to write the spatial parts. Now for helium atom, in the you have two electrons. You know that the ground state corresponds to ground state, both electrons are in 1s orbital. Okay, so both the electrons are in 1s orbital, and since both the electrons are in the same spatial orbitals, okay, their spatial orbitals for both the electrons are the same. So the spatial orbital, so you can write psi spatial of R1 R2 is equal to 1s of R1 times 1s of R2. Okay, so the spatial parts are the same, and so the since each electron is in the 1s orbital, so the wave function in the orbital approximation can be written as a product of wave functions. This is 1s for R1, this is 1s for R2. Okay. Now if both the electrons are in the same spatial orbital, okay, since the product of the wave functions has to be antisymmetric, you can immediately see that this is the only allowed spin function. So only one spin function is allowed, that is the antisymmetric spin function. So you can immediately write that psi of 1 2 is equal to 1s of R1, 1s of R2 into 1 by root 2 alpha of S1 beta of S2 minus alpha of S2 beta of S1. Okay. You can immediately write this form, and you can write this in a slightly different form. Suppose I take the 1s inside, I can write this as 1 by root 2 1s of R1 into alpha R1 times 1s of R2 beta S2 alpha of S1 minus, so I will put these in brackets and it will be clear why, 1s of R2 alpha S2 times 1s of R1 beta of S1. Okay. So, you can write it in this form, and notice that this depends only on electron 1, this depends only on coordinates of electron 1. So, I can write this as 1s alpha of 1. So, I just denote this as this is the spin orbital of electron 1. So, this says that the spatial orbital is 1s and the spin orbital is alpha. So, 1s alpha of 1. I can write this as 1s beta of 2 minus 1s alpha of 2 1s beta of 1, and this whole thing times 1 by root 2. Okay. And this can be written as 1 by root 2 1s alpha 1s beta alpha 1s beta. Sorry, I will put it slightly differently. I will write 1s alpha, 1s alpha, 1s beta, 1s beta. Okay, and okay, so the first row I have 1s alpha, and the second row I have 1s beta, and what I am going to put here is in the first column I will put 1, second column I will put 2. Okay. So, it is 1s alpha 1 times, so this determinant gives me the allowed wave function. Okay. So, this determinant is called the Slater determinant. Okay. So, the Slater determinant, notice that I put all the spin orbitals on the rows, and I put the coordinates of the electron in the columns. Okay. So, the first column corresponds to coordinates of electron 1, okay. The second column corresponds to coordinates of electron 2. Now, writing the wave function in the Slater determinant form is very useful, and it ensures that if I switch 1 and 2, if I switch the coordinates of 1 and 2, it is like switching 2 rows of a determinant. It is exactly equivalent to switching 2 rows of a determinant, and so when I interchange 1 and 2, then I am changing the sign of the determinant. Okay. So, the Slater determinant, it ensures that your wave function is antisymmetric. Okay. So, it ensures that the wave function that you have is antisymmetric, and you can do this even for this need not be, it can be if both the electrons. Okay. So I can do this even for other this does not need to be 1s alpha and 1s beta, it can be 1s alpha and 2s beta. Okay. So you can do this for more complicated systems rather than just helium atom. Okay. So it ensures, because of the nature of this determinants, it ensures that that the total wave function will be antisymmetric, and the reason it will be antisymmetric is that switching the coordinates of any 2 electrons is like changing 2 rows of the determinant. Okay. So this can be extended to a many electron system, and you can easily show how to extend this to a many electron system, and that is what we will do next. So incidentally, you notice that the moment we said that the spatial parts of the 2 electrons are identical, okay, when the 2 electrons are in the same spatial orbital, because of the antisymmetric condition, their spins had to be different. Okay. So having 2 electrons in the same spatial orbital ensures that the spins are different, and this is an illustration of Pauli's exclusion principle. Okay. So Pauli's exclusion principle says that if 2 electrons are in the same orbital, then their spins have to be opposite, and so these two electrons are in the same spatial orbital and their spins are opposite. Okay, and that is the only allowed state. Okay, only allowed wave function. Okay, now suppose you had a many electron system. How do you write this? Okay, so suppose you had psi of 1, 2 up to n, and for convenience let us assume that this is a closed shell system. Okay. So, closed shell system, that means n is an even number and all the electrons are paired in their orbitals. So, in this case what you have is you have various you can write this determinant in this form 1 over square root of n factorial. Okay, that is the normalization constant, and then if the various orbitals correspond to phi 1 alpha, phi 1 beta, phi 2 alpha, phi 2 beta, all the way up to phi n by 2 alpha, phi n by 2 beta. So, all the electrons are paired in their respective orbitals, and these are the various orbitals. Okay. So, we can write the Slater determinant very easily. So, you write all the orbitals in this way. Similarly, you will write the same orbitals beta and so on all the way up to, you will write it n times. Phi 2 alpha. Okay, now we have to write the various arguments. You have to write the various, what is it a function of. So, we have to fill in these things. Okay, and following the prescription for the Slater determinant, you in the first column I will put 1 corresponding to electron 1, second column I will put 2 corresponding to electron 2, and so on. I will go all the way. In the nth column I will put n corresponding to electron n. So, there are n electrons in n by 2 orbitals. Okay. So, there are n electrons and the total number of orbitals is n by 2, and so you follow this prescription and you can write the wave function, and this is antisymmetric to interchange of any two electrons. So, I can switch 1 and 2, I will get, it will be antisymmetric. I can switch 1 and n, again the determinant will change sign. So, if I change any two rows of the determinant, then the determinant changes sign, and the way we have written the Slater determinant, we have ensured that the coordinates of only one electron appear in one column, coordinates of only one electron appear in any column, and that ensures that switching two columns is like changing the coordinates of two electrons. Okay. So this way of writing determinants is extremely useful for closed shell systems, and it is not just atoms for which this is useful. This is also useful for molecules with which have a closed shell configuration. Okay. And so this is a very simple and very useful application of this idea of determinants. Okay. The next application that we will do is what is called as Huckel molecular orbital theory, and this is another application of determinants. Okay, and in fact in general of matrix methods and linear algebra. Okay, now in order to introduce Huckel molecular orbital theory, I will first tell about molecular orbital theory, and in particular about what is called as linear combination of atomic orbitals leading to molecular orbitals. So if you have a molecule, okay, so suppose you have a molecule has many electrons. Okay, a molecule typically has many electrons, and so you have coordinates 1 to up to some number if there are n electrons. Okay, so this is a molecular wave function. So this is the wave function of the molecule. And in particular, I should say this is the electronic wave function of the molecule. So this is the electronic wave function of the molecule, and the first thing you do is to write this as a product of one electron wave functions. So you write this as a product of n, and these are single electron wave functions. These are called orbitals, and in particular these are called molecular orbitals. Okay, so this is under the orbital approximation. So we use the approximation that the total wave function can be written as a product of these orbitals or single electron wave functions. Okay, now the molecular orbitals are actually incredibly complicated objects to calculate. Okay, and what is typically done is a procedure called linear combination of atomic orbitals. Okay, it's called LCO-MO. So linear combination of atomic orbitals giving molecular orbitals, and this is implemented in something called a variational procedure. Okay. So what are the main steps in this procedure? So your molecular orbital, I'll call this psi MO. Okay. So your molecular orbital psi MO is written as a sum of Ci phi I. Okay, this is the coordinate of the electron. Okay, and I'm restricting only to the spatial part. Okay, so restrict only to the spatial part. So the molecular orbital is a function of coordinates of one electron. I just call that coordinate r. Okay, and that is written as a linear combination of various functions. Okay, these are various functions, and so it's written as a linear combination of various functions. So you can write this as C1 phi 1 of r plus C2 phi 2 of r plus and so on. Okay, so you're summing over I. Okay, so this is the basic idea, that you write a molecular orbital as a linear combination of various functions, and these functions we choose as atomic orbitals. Okay, so these functions are chosen as the atomic orbitals, and typically when you have a bond, then you choose them as the orbitals of the atoms corresponding to the that produce the bonds. Okay, so if you have a bond between two hydrogen atoms, you choose these to be atomic orbitals centered on the two hydrogen atoms. Okay, so for example, if you have H2, okay, so I can write this as the first atom I show as A, second atom as B, and if you have an electron whose coordinate is r, okay, then the wave function of this electron it's in a molecular orbital, and its wave function is written as C1. Now corresponding to the atomic orbitals at A. So the atomic orbitals These are on different atoms. Okay, so this is a linear combination of atomic orbitals on different atoms. For a hydrogen molecule, the lowest energy state will correspond to overlap between 1s of A and 1s of B. So you write this as C1 times 1s A of R plus C2 1s B of R. So this basically corresponds to a 1s orbital centered at A. So it's a 1s orbital assuming that the nucleus is at A. So and this corresponds to a 1s orbital assuming that the nucleus is at B. Okay. So assuming that the nucleus is at B, what does 1s look like, and what is the value of that at R? Okay. So this is how you write a molecular orbital wave function. Okay. So notice that this is a sum of atomic orbitals. Okay, there is only one coordinate R because this is a single electron wave function, and so the coordinate of that electron appears. Okay, so there is only one coordinate R that appears. Okay, but these atomic orbitals are centered on different atoms. Okay, so 1s centered at A will be some constant. So this will be some constant times e to the minus z times I'll say R A divided by A naught. A naught is a Bohr radius. So R A is the distance of R from A. So this is R A, and if this is R B, so the other, similarly this will be C times e to the minus z R B by A 0. Okay. So they are different they are since they are centered at different atoms, the resulting function will be different. So this will depend on this distance, whereas that will depend on where the 1s A will depend on this distance, 1s B will depend on this distance. Okay. So this is a general linear combination of atomic orbitals procedure. Now the question is, how do you calculate your C1s? How do you go about calculating your C1 and C2? What is the choice of C1 and C2 that you should take? And the choice of C1 and C2 is given by something called a variational procedure. So the variational procedure will give you choice of C1 and C2. So the choice of C1 and C2 is given by a variational procedure. Okay, so how does this work? So this is based on something called the variational theorem that says that if you calculate the energy of any trial wave function, then it is always greater than or equal to the true ground state wave function. Okay, so then the best choice of C1 and C2 will be that choice of C1 and C2 that gives you the minimum energy. So the minimum, so the choice of C1 and C2 that gives you the lowest energy turns out to be the best choice of C1 and C2. Okay, so we calculate the energy of this of an electron in this molecular orbital. Okay, and in fact you have to calculate the expectation value of energy. Okay, the expectation value of energy is given by psi mo of R Hamiltonian operator psi mo of R, okay, integral dr divided by psi mo of R psi star psi mo of R. Okay, so this is the definition of the expectation value of energy, and so you go ahead and you calculate this. Now wherever I have psi mo, I substitute this value, and if I go ahead and do that, then I'll get here here I have C1 1sa plus C2 1sb. Okay, so I'll have C1 star 1sa star of R1 of R plus C2 star 1sb star of R. Okay, so that is this psi star times Hamiltonian operated on C1 1sa of R plus C2 1sb of R dr divided by the same thing as the numerator without this h. So I'll just write it as here. Okay, so it's exactly the same as the numerator without this h. Now we have 4 terms in the numerator and 4 terms in the denominator. The numerator will consist of terms of the form, if I exclude the constants, it will contain terms like 1sa of R, h 1sa of R, integral dr. Okay. So this term we call it as HAA. HAA, it's independent of R, it is just some number, we call this HAA. Similarly, if you have 1SA and 1SB, we will call it HAB. So if you had 1SA H, 1SB, we will call it HAB, 1SB H, 1SA, we will call it HBA. Okay, so you say 1 is B star or H 1 is A or dr. Okay. This is HBA and this is the same as HAB, which is 1 is A star of R H 1 is B of R. Okay, so because your Hamiltonian is a Hermitian operator, it satisfies this property. Okay. Similarly, we can define HBB also. Okay. So then your E, your expression for E, at least the numerator part, we can write in terms of HAA, HBB, and HAB. For the denominator, we will use exactly a similar notation, but if there is no H, we will call it SAA. So if you had 1 SA star or SAB. If you had 1 SA and 1 SA, if you had 1 SA, 1 SA, that is SAA, which is just 1. Okay, so of R equal to 1. Similarly, if you had 1 SB, 1 SB, it would be 1. Okay, so now you can write your expectation value of E as C1 star. So the first term will be C1 star C1, 1 SA H 1 SA. So that is C1 square H AA. The second term will be C2 square H BB, and you will have a term that I'll write it as 2 C1 C2. Okay, so you have C1 star C2 and C2 star C1. Okay, and if C1 star C2 is the same as C2 star C1, so you can write it as 2 C1 C2 H A B. Okay. So let's for simplicity I have assumed that C1 and C2 are both real. Okay. So if C1 and C2 are real, I can write it in this form, divided by, now in the denominator I'll get C1 square plus C2 square plus 2 C1 C2 S. SAB I'm just denoting as S. Okay. So the variational theorem says that this energy should be minimum. Okay. So you should choose your C1 and C2 such that this energy is minimum. So in other words, your dou E by dou C1 equal to 0. Okay. And if you calculate dou E by dou C1, so we'll go ahead and do this. We'll just call this some numerator divided by denominator. We'll call this denominator and this as numerator. So you can use the usual rule for differentiation, and you can write this as denominator into derivative with respect to C1 of this is 2 C1 HAA, and you have C1 here also, so you have plus 2 C2 HAB minus numerator into derivative of denominator, in this case will just be 2 C1 plus 2 C2 S divided by denominator square. Okay. And what I can do is I can take one of the square of the denominator up, one of the square of the denominator I'll take, so I get 2 C1 HAA plus 2 C2 HAB. Okay. And then I have an n by d. N by d is nothing but E. N by d is nothing but this E. Okay. E times, I'll have 2 C1 plus 2 C2 S divided by denominator. Okay. And if this has to be equal to 0, then basically you will say that this numerator has to equal 0. So this has to equal 0. Okay. So if this has to equal 0, I can write this as C1 times HAA minus E plus C2 times HAB minus E S equal to 0. Okay, so I can write this in this form. So I cancel the 2, I cancel the denominator. So I have C1 times HAA minus E, and I have C2 times HAB minus E times S. Okay. And if you do the same for dou E by dou C2, what you will get is the following. You will get C1 times HAB minus ES plus C2 times HBB minus E equal to 0. So if you do the same for dou E by dou C2, you will get this equation below. So now you have two equations and your two unknowns are C1 and C2, but the right hand side of both the equations is 0. Okay. Now these equations have a trivial solution, C1 equal to C2 equal to 0. So trivial solution, C1 equal to C2 equal to 0. So if I put C1 and C2 as both 0, then I satisfy this equation, but that is not really a useful solution because C1 equal to C2 equal to 0 means your wave function is 0 and there are no electrons. So non-trivial solution, so the condition for non-trivial solution is that this determinant, the secular determinant, equal to HBB minus E has to equal to 0. So, the condition for non-trivial solution is that this determinant has to equal 0. Okay. Now, this gives a simple so if you go ahead and multiply out this determinant, what you will get is a quadratic equation in E. So, you will get this into this minus this into this. So, minus HAB is the whole thing square equal to 0. So, this is a quadratic equation in E, in expectation value of E, and if you solve this, you will get the expression E is equal to, you will get two solutions. Okay, so, the two solutions are E plus and E minus, okay, and E plus and E minus are related by this way. So, this is EA plus or minus, or okay. Okay, so let's go work this out. Okay, so if you take this, you will get E square, and from here you have a E square S square. Okay, so E square into 1 minus S square plus E, okay, and the terms containing E are given by, so you have a minus HBB minus HAA, and you have, so you have minus HBB minus HAA minus, now in this case you will have plus twice HAB S. So, these are the terms multiplying E, okay, and then the terms that do not have any E are given by, so plus HBB. So, you have one term HAA HBB, and then from here you will have HAB square. So, minus HAB square equal to 0. Okay. So, this is a quadratic in E, and you can solve this to write the value of E. Okay. Now, we won't do this in detail, but you can solve this and you will get two values for E. Okay. We will take this for the specific case when in this case, since both the atomic orbitals were 1s orbitals, so HAA equal to HBB. So, in the case HAA equal to HBB, and we will just call this EA. Okay, so, if HAA equal to HBB equal to EA, then you can write E. There are two solutions, plus and minus solutions, and this is given by EA plus minus HAB divided by 1 S. Okay. So, there are two solutions. Okay. So, there are two solutions, and the two solutions are related this way. So, in other words, you can write E plus is EA plus HAB divided by 1 plus S, and E minus EA minus HAB divided by 1 minus S. Okay. Now, usually S, depending on the sign of S, one of these is lower and the other is higher. Okay. And okay, so depending on the sign of S and HAB, one of these is higher or lower. Okay, so now what Huckel had done was to use this molecular orbital theory and for in a very creative way to describe pi conjugation in aromatic systems. So now we'll see an application of this in what is called as Huckel molecular orbital theory. Molecular orbital theory, and this is used to describe pi conjugation So systems that have pi conjugation. So this Huckel molecular orbital theory is used to describe these systems. So Huckel in Huckel molecular orbital theory, you restrict to pi molecular orbitals Okay, so for example, if you have butadiene, okay, so you have a pi conjugated system. Now Huckel molecular orbital theory gives a simple way to calculate the energies of the pi molecular orbitals, of only the pi molecular orbitals, okay, not the sigma orbitals, okay. And these are actually simply related to the highest occupied molecular orbitals. So that's the reason why Huckel molecular orbital theory is so useful. Okay, so in order to see how to do Huckel molecular orbital theory, there are just two ingredients that we need. First is we need to write the secular determinant for a system, for this system. Okay. So in Huckel molecular orbital theory, you write you have various atomic orbitals centered at each of the atoms. So you have so if you call it 1, 2, 3, 4 atoms, you have atomic orbitals centered at each of these atoms. And if you follow the molecular orbital prescription, you can write a wave function and you can write the secular determinant. So following the molecular orbital theory, you write the secular determinant. So for example, if you have butadiene, 1,3-butadiene, you will write as H I'll say 1,1 minus E H12 minus E S12 H13 minus E S13 H14 minus E S14. Okay, and these are S is the overlap of the pi atomic orbitals of 1 and 4. Okay. Similarly, the second row will be H21, which is same as H12 minus E S12. The second row, second column will be H22 minus E H23 minus E S23 H24 minus E S24. Okay. And this is H13 minus E S13 H23 minus E S23 H33 minus E H34 E S34, and this will be H14 minus E S14 H24 minus E S24 H34 minus E S34, and finally H44 minus E. So notice that the two off diagonal elements are identical. Okay, all off diagonal elements are identical in this picture, and this has to be equal. This has to be equal to 0. So you set this equal to 0, and you get some polynomial in E. Okay, and you solve for the energy. Okay, so now in Huckel molecular orbital theory, so Huckel approximations Okay, so in the Huckel approximations, H11 equal to H22 equal to H33 equal to H44 equal to alpha. Okay, and Hij equal to beta if I and j are bonded. So 1 and 2, H12 will be beta, okay, and equal to 0 otherwise. But H13, because 1 and 3 are not bonded, will be 0. Okay, and then Sij equal to 0. So Sij is always 0. Okay, so this was the simple basis of Huckel. With this simple approximation, this determinant simplifies to, can be written as alpha minus E beta 0 0 beta alpha minus E beta 0 0 beta alpha minus E beta 0 0 beta alpha minus E. Okay, and this will be equal to 0. Okay, so notice that alpha minus E along the diagonals and beta is just next to the diagonals. You have these betas. Everywhere else you have 0. Okay, and this theory can be extended to much larger systems. I just took 1,3-butadiene, but you could extend it to benzene. You could extend it to other conjugated polyenes, and this works. And so what you can do is you can calculate E. Okay, so if you set this equal to 0, you will get a 4th order polynomial in E, and you can easily calculate this, and you can show that E is equal to alpha. So it has 4 values. One value is alpha plus 1.62 beta. The other is alpha plus 0.62 beta, alpha minus 0.62 beta, alpha minus 1.62 beta. So you get 4 values. Okay. Now it turns out that beta is negative for this system, so this is the lowest energy. And this is the highest energy. Okay. Now what is so interesting about these values is the following. Now butadiene has 4 electrons. So butadiene has 4 electrons. Okay. So 2 of them will be in the orbital corresponding to this, and 2 of them will be in the orbital corresponding to this. So the total energy is equal to twice alpha plus 1.62 beta plus twice alpha plus 0.62 beta. Okay. This is equal to 4 alpha plus 4.48 beta. Okay. This will come out to this value. Okay. Now this 4.48 is actually quite interesting, and the way to understand why this is so interesting is the following. Remember, beta is negative. Okay. To see the significance of this 4.48, you ask yourself what will happen if you just had ethylene. If you just had ethylene, and if you do the calculation for ethylene, you will get the lowest energy is alpha plus beta. This is lowest. So you do the same calculation, you'll have only this term. Okay, so you can have alpha plus beta or alpha minus beta, and the lower energy corresponds to alpha plus beta. Okay, so if you had 2 pi bonds, the energy, if you just had two pi bonds, okay, then the energy would have been 4 alpha plus 4 beta. Okay, and so this energy is actually greater than 4 alpha plus 4.48 beta. Okay, so that means the energy of butadiene is lower than that of 2 separated pi bonds. So if you had 2 separated pi bonds, the energy would have been 4.48 beta, but this is lower than 2 separated pi bonds. So it is not as though, so this would have energy of 4.48, whereas in this case, because the electrons are delocalized, there is some delocalization, and that allows you to have an additional lower energy. So the difference in these two is 0.48 beta. This is called the delocalization energy. Okay. So Huckel molecular orbital theory gives you a simple way to see this idea of delocalization and this delocalization energy, or sometimes it's even called resonance energy. And you can take this one step further. You can calculate all kinds of atoms. For example, you can do for benzene. This versus where the electrons are truly delocalized. Okay, and in this case you will get a stabilization of 2 beta. Okay, and so benzene has a very large delocalization energy. Okay, so this is a simple application of the idea of determinants and linear algebra, and this completes the linear algebra part of this course, and starting from the next lecture we'll start differential equations.